in 1990 by Carver Mead, and he and Misha Mahowal were really trying to do basic research to try to use the physics of silicon to understand the function of neural circuits. So it was really fundamental research, and the idea was using the physics of the transistors, the devices that you can implement in CMOS to reproduce the physics of the biophysics of real cells. And of course, because we have CMOS, we can also use digital circuits, and because also neurons, whenever they spike, it's an all or none event. The idea was to use both analog and digital to really build, understand by building. And this is something that we are still carrying on, and some of the colleagues in the community are still carrying on. In Zurich in particular, we try to really study small parts of the brain. So we really look into neuroscience deeply, by, for example, looking at the visual cortex or the auditory cortex or hippocampus. This is an example of a picture taken from Area 17 of the cat visual cortex by Nuno da Costa in 2008, where he highlighted a small number of neurons. And by looking at the statistics, we can then figure out how these neurons are connected and then try to reproduce those in silicon. So we do use subthreshold analog circuits. We teach analog circuits, and we use them in a way that is using physical variables and physical time. So this is something also that is completely different from normal computing. If you think about it, in a computer simulation, physical time is completely detached from your software simulation time. You could be simulating evolutionary processes that in biology take centuries in a few milliseconds, or if you want to do protein folding or some simulating complex dynamics, it might take one night to run through the code, whereas a protein folding in biology might take a few milliseconds. So they're completely detached. But here, when we build these electronic systems, we let time represent itself. I'll show you better what I mean by that. And of course, we cannot imagine to observe intelligence emerge out of a piece of silicon sitting on a table. In order to see if there is anything that is related to cognitive processing, we need to connect these electronic systems to sensors and actuators. So we need to have something that can really interact with the environment, and we try to build systems that interact in a closed loop in real time. So then we can explore, the abilities of these agents to carry out processes in a way that might look like intelligent. So that's everything is related to real physical world, real physical signals, and completely different from virtual digital data that's stored on a hard disk. This is the approach we take. And just to reiterate this idea that neuromorphic, at least in my view, is related to these points. There is a paper that I recently published. I was invited to do a perspective, and so it was the opportunity for me to rant and give you and tell what I think is wrong with the current use of the term neuromorphic, and maybe how we can adjust to go back to the original ideas. So there is a rant there that I published just a few weeks ago, actually. Anyways, going back to the title of the talk, Principles of Neural Design, I just want to highlight again differences between standard computing and biological computing. And one of the biggest differences you can see here in a plot that was produced by IBM, where this is already very old. You see some processors, that, in fact, many IBM processors, but also Intel, that have a high clock frequency. We go into megahertz and gigahertz, and do a lot of computation, but at the cost of a lot of power consumption, high power consumption. So the power density is on a log scale here on the y-axis. And you see there's a huge difference. This is a logarithmic scale, both on x and y. So there's a huge difference with the way that animal brains compute. So animal brains use extremely slow elements. In addition, we heard about heterogeneity. They use noisy and variable processing elements, whereas in processors, everything is bit precise. Every transistor has to be either on or off, and if one of these doesn't work, you have to throw the whole chip away. Also, the computing substrate of the brain uses distributed processing across space, different from phenomenon architectures where you have the CPU on one side and memory on the other, in a massively parallel operation. You might argue GPUs and CPUs now have 8 cores, 32 cores, 64 cores, but this is very, very different from the 10 to the 11 neurons that are all working in parallel in the brain, and the 10 to the 14 synapses that are integrating all the spikes in parallel. Having said that, these 10 to the 14 synapses and 10 to the 11 neurons are not connected all to all like you would imagine in a deep network. There is a very strict wiring constraint in the brain as well. And so typically the neurons are connected with a high density with nearby neurons and lower density that decreases exponentially with distance with faraway neurons. And this gives rise to small world networks and local connectivity. And that's something that could be used to carry out computation. Maybe it's not an epiphenomenon, it's really something that improves computation. So it's also something to keep in mind. And also, if you think about it, biological computing systems are always on. You don't first train them and then you do inference. It's always processing data and always adjusting and adapting to the changes in the statistics of the data. So there is this continual learning that also in AI now is becoming important. But this is something that's natural in animal brains. And as I said, this learning is tightly tied to the fact that we have closed loop interactions with the environment. So in AI, everyone is obsessed with accuracy. You want to have 99, 100% accuracy. But if you think about it, if you're trying to do reaching movements with robots, and you have closed loop interaction with feedback, all you need is 51% accuracy. I only need to know that my target object is to the left or to the right of my body, and then through feedback I can adjust. If I see that there's a mistake, I can always adjust because of this continuous feedback loop that allows me to correct. So you don't need high accuracy because we're not doing ballistic type of movements. If you're interacting and if you have negative feedback, accuracy is not the most important factor. Maybe latency and other factors are important, but we don't have to fight with AI saying, oh, I can do classification with this accuracy if we have a system that can close the loop with negative feedback. And finally, the time represents itself argument I was telling you before is that if we match the dynamics of the signals coming in, the data rate coming in, with the dynamics of the computation, we don't need to store information and go and get it when we need it. We can process information in a streaming mode. As it's coming in, we can process it, and then we do the action, then we take the next input and we do the right action. In that case, you save a huge amount of power because you don't need to move data from memory to processing. You process it as it comes, and then you can sort of synchronize your computation with the natural data rate of the incoming events and save power. So the computation is really exploiting the natural time evolution of the physical elements in your computer, in your neurons and synapses. So you really take advantage of the substrate to carry out computation without having to store data continuously. And to show you that we can use silicon to do that, very, very much like neurons do it in biology, I just have this one slide to show you that if you have a transistor and instead of just using it fully on or fully off, where you have a lot of current or a very small amount of current, you can actually, this is what Carver Mead was saying, you can have a graded input and you can look at the graded output. Now, if this is analog computing, it's been around since the 50s, it's not neuromorphic at all, but most of the analog designs are typically using the transistors in the above threshold regime, where you can still have some analog input and you get an analog output. This is a semi-log plot also. The nice thing here is that if you have some noisy signals, you compress the noise and you can have hi-fi, high fidelity equipment. You pay because you get milliamps, so you burn milliwatts or tens or hundreds of milliwatts. And no one was using the transistor in this regime when doing these hi-fi types of circuits, A to D amplifiers and so on, because if you have the same amount of some millivolt fluctuations in the input, it would give to a huge difference in the output. So these circuits in this region are very, very sensitive to noise. However, they are also very, very low power, because if you use nanoamps, then you get tens of nanowatts or hundreds of nanowatts, or you could even go lower, in fact. And Carver Mead was saying, neurons work in this regime. They work because of diffusion, Boltzmann statistics, so you get exponentials, and if you have a line on a semi-log plot, you have a pure exponential. So because neurons can do processing robustly, despite this noise sensitivity, maybe we can build systems that, even though the single element is very noisy, at the system level, with feedback and learning, we can cope with this noise and then have low power. So this was the idea, the original idea. And of course, it was inspired by the fact that neurons and transistors, when they work in this regime, they have the same physics. If you look at the data from Hodgkin and Huxley, when they were trying to explain how ion channels produce action potentials, they were measuring exactly the same type of plots on a semi-log scale with millivolts on the x-axis and then conductance or current on the y-axis. And again, ions flow through proteic channels because of diffusion gradients, and in this regime, electrons and holes flow through the transistor channel because of diffusion gradients as well. So it's the same physics. And by using that, then we can build chips that really have the same behavior of real neurons. And that's what the community has been doing. Many of us here have been doing chips for many years. We've been also doing those chips in the Institute of Neuroinformatics in Zurich. This is an example of an old chip that was designed actually at the times in which Elisabetta was doing her PhD in Zurich as well. And you can see the architecture is always the same. You typically have a vector or a column of neuron circuits, physical circuits. So if you have 10 neurons, you have to copy paste 10 times the same circuit. If you have 100, you copy paste 100 times. And then each neuron has a number of synapses. It could be 32, 64, 256. But then because you have many neurons, then you have a matrix of synapses. And the synapses are not just weight multipliers like you would have in a deep network. They're actually complicated circuits that have complex dynamics with nonlinearities, and of course they also have different weights. You can set the weight. If you add learning circuits, you can change the weight directly on the synapse. So this is a typical example of in-memory computing. If you think of this as a memory element where you store on a capacitor or in an SRAM register the value of the weight, then by sending spikes to it and having signals coming back from the neuron, you can change the weights and you can do processing in memory, inside the synapse. And so we build these spiky neural network chips using these subthreshold analog circuits. All of the transistors here work in this analog subthreshold domain. And because they're working in the subthreshold domain, they are slow. I will show you how we can get really biophysically realistic time constants. So silicon likes to go at megahertz, from our cell phones and our computers, but we manage through judiciary design to slow down silicon. It's not easy to go to fractions of hertz or single-digit hertz. And all of these are by construction, they're all parallel. They're copy-pasted. If you send a spike to a whole column, then all of these synapses will integrate at the same time the same spike, and they work in parallel. This is old technology, so it's pure CMOS, but we have also in the audience people that have been replacing these elements with new emerging memory technologies, and we've heard about from also Arindam resistive memories, but there's a whole zoo of devices that you can use to replace, shrink CMOS synapses with ferroelectric, with spintronics, with resistive memories, and so on. However, remember, they are imprecise and noisy. They are still using these transistors that are sensitive to noise, and because they're analog, whether you use memoristic devices or analog transistors, even though you copy-paste exactly the same layout, when you fabricate them, they will have slight differences. And so each synapse, each neuron will behave in a way that is different from the other synapse, the other neuron. Typically, with these types of designs, we have a coefficient of variation of about 0.2. So if one neuron fires at 100 hertz, the next neuron might fire at 120 hertz, and the other one maybe at 80 hertz, and so on. This is the type of variability we cope with without trying to optimize it. Of course, if we increase transistor sizes, we can reduce that. But we don't want to. We want to use the same type of variability that is measured in the nervous system. And people, ask us, if computers can go so fast, why do you slow down? And if, backprop works, AI is solving so many problems, why do you want to use analog and not digital? There's many answers, but if you compute through the dynamics of the circuits, you can save power. You can really go from 300 watts of a GPU to microwatts of a dedicated edge computing accelerator. You don't need to count time. If you don't use digital and use analog, you can just avoid all the clock trees and all the complexity that comes with introducing megahertz or gigahertz clocks. We saw from Arindam that if you do need to use digital, you need digital to analog converters or analog to digital converters, which take up area and power. So if you do everything in analog, you can avoid that. Because these transistors work with nano or picocurrents, the heat density is very small. So even any place on the chip will have a very, very small amount of heat, which means that then if you start to use these emerging technologies that stack multiple layers on top of each other, not only 2, but 3, 4, 5, 6, like a whole cortex, then you can actually use this technology. If you had digital transistors, you wouldn't be able to. You would need to have heat sinks everywhere to dissipate the heat and bring it outside if you have a volume of transistors. So then we can exploit the full potential of device physics, not only CMOS, but memristors, and even there is a whole new field of neuromorphic organic colleagues that are looking at organic devices to do neural networks and spiky neural networks. The disadvantages, there's no free lunch. Everything comes with a disadvantage. Remember, if you need 100 neurons, you need to copy 100 times the same neuron. If you need 1,000, you need to use 10 times more the area. And you imagine, if you need to scale up to 175 billion parameters like ChatGPT, you would need a chip that is as big as this whole floor here. So that's something we cannot do. Remember, there is the variability. There is still this problem of noise and variability. How do we do robust computation? I'll show you that in a few slides. This is just to give you an example of a synapse. It's a handful of transistors, but you do send in spikes in input and you get currents in output. This was designed by Chiara Bartolozzi, who's coming here tomorrow, when she also was a student at INI, and myself. It's so simple, you can actually derive the transfer function and the equations. And now you see here from the definition of the time constant how we can slow down silicon. Because if we have 1 picofarad capacitor and 1 picoamp current, the pico and the pico cancel out. UT is the thermal voltage, which is 25 milliseconds at room temperature. Sorry, millivolts at room temperature. Kappa is a subthreshold slope factor, which is about 0.7. So by using 1 picofarad and 1 picoamp, we get about 30, 35 milliseconds time constants. And you can see it here, right? You can see that we have millisecond time constants in the data measured from the chip with one synaptic weight or another synaptic weight. And in the inset, you see data from a real synapse, measured from a real biological synapse. And I hope you appreciate the same sort of range of values. Here we have nanoamps because the oscilloscope was aliasing for smaller currents, but we could easily go down to picoamps and have really exactly the same type of outputs that real biological synapses have. So this is really showing that the physics of these devices are very similar to the physics of real synapses. And for neurons, you have the same type of circuits. It's a bit more complicated. There is more. This is the latest neuron, which is even more complicated. There's many more transistors, but you might recognize the same type of differential pair with a capacitor, another differential pair with another capacitor. So it's the same building blocks. And if you can use these as channels. So you could use these as calcium channels after hyperpolarizing current, sodium channels, potassium for the positive feedback, potassium channels for the negative feedback. And you really get outputs that are resembling real spikes from real neurons with the same time constants and the same, the voltage here is amplified because we have these amplifying parts. But we do get the same time constants for doing neural computation using these devices. And another argument that AI colleagues always come up with, why analog is one, but the other one is why SNNs? Why are we bothering with spiking neural networks when artificial neural networks are already doing such a great job? And I agree, if we need to simulate, if we need to do ChatGPT, or we need to recognize cats from dogs, pictures of cats from pictures of dogs stored on a hard disk, ANNs are already doing the best. So doing SNNs, I don't think is going to bring a bigger advantage. And doing SNNs on a standard microprocessor is not going to save power, significant amount of power either. So using spiking neural networks to replace AI algorithms is not the best approach. But remember, we are not trying to do that. We are actually building physical systems that interact with the environment. So this is the thing. We're trying to do some real-time signal processing system that gets real data, temperature, auditory signals, visual signals, and then makes a decision and action based on that data. And we want to do this in a way that is robust through noisy communication channels. So the microphone, the temperature sensor, the pressure sensor has to send this analog data to the processor through some noisy communication channel. We want to do this with a chip that can do it with local processing, maybe multi-core architectures, and we want to save power and latency. So if you take all of these ingredients and you go to any communication lab or division, any engineering and signal communication, they will tell you what you need to do is you need to modulate signals, digitize them, and then use some form of modulation. And what biology found is that pulse frequency modulation is one way to go. So if you convert your analog signals into a sequence of pulses, spikes, and the rate of the pulses is proportional to the amplitude of your analog signal, you can have the optimal communication transmission method from information theory point of view. So if you just study information theory, it will show you that either you do pulse frequency modulation or amplitude modulation. Some form of modulation and discretization will allow you to transmit these analog signals in a robust way, minimizing power and latency. And evolution found the same solution. If you think about it, neurons are there from the smallest cockroach to the biggest elephant. So this idea of converting analog signals into spikes is something that is a winning strategy that evolution found across the whole animal kingdom. And even if you're doing computation, this is Mike Davis from Loihi, it turns out that once you have spikes, because you need to have spikes to transmit, but once you have them, doing computation with spikes actually brings extra advantages that one had not thought of. So counterintuitively, once you have spikes, you can also use those for doing computation. And so that's what we're doing, and we are using neurons, remember now, how do we do robust computation using these neurons? Keep in mind that neurons, both in biology and in silicon, are highly variable. We already saw examples of how the morphology of the neuron really changes from the previous talk just last week. And this is another slide from Bartlett Mell when he was at Caltech with Ernst and I, where he's highlighting the differences. You get your Purkinje cells, your pyramidal cells, your interneurons, and they have different. There's always a cell body. There's always an input structure, the dendritic arborizations, and then there is an output structure, an axon, which is actually not shown here, but the axon would really go out of the slide and out of the room. It's much longer than the dendrite at this scale. And because of the difference of the geometry and the morphology, each one of these neurons has different properties. And so the question is, how can our brain and how can we build systems that have these differences and still do robust computation? There is a lot of theory that has been coming out, and in the last actually 2-3 years, there's been a whole series of papers that show how you can do robust computation using heterogeneous elements. In this case, this is from our group, from Dmitry Zendrikov. In this case, it's with transistors, but there is more and more showing how you can do it with computer simulations of brain-inspired networks, You can get reservoirs of timescales if you have heterogeneous neural assemblies. You can get robust computation if you use dendrites with jitter, with variability. You can get improvement in learning if you have heterogeneity. You even improve accuracy in learning with spiky neural networks, and so on. So you can get multiple timescales if you have heterogeneity. You can have efficient processing if you include delays. You can do robust computation, and all of these things sort of culminated in this paper that was also advertised last week, Saturday, by Rijikesh, of a neuron paper that just came out a few weeks ago on how heterogeneity shapes computation in the brain. This is just to tell you there is hope. There is theory that shows how you can use variability in your computing substrate to do efficient computation. So you don't have to give it up. You don't have to use digital. You can actually try to live with the fact that you have a variable computing substrate. And this is what we have. So this is data from one of our chips where we send exactly the same input to all the 256 neurons of the same core, identically designed, but then when they're fabricated, they're different. And you see that the time to first spike differs depending on which neuron the spike goes to. And if you realize it, the variability, the coefficient of variation here is about 0.2, like I was telling you. If you take a lot of spikes in input and you measure the spikes in output, you see that the neurons are all over the place. It's really not precise at all. I would never use this chip to control my airbag or to do my balance in my bank account, right? This is really, really terrible. If you average, you get a nice ReLU. But if you have to count on any one of these neurons, you could be anywhere in the place. This could look like a disadvantage. If your argument is, I want to copy biology, this is a feature. If you look at real data from real cortical cells, which is this inset here, they have very similar type of variability. So also real neurons have to do robust computation with this type of variability. And how can we do that? Well, there are two strategies that come to mind. One is to use populations, so you average. And the other one is to use adaptation and learning. So from the point of view of populations, we actually tried to characterize this variability. And we said, what if we take 2 neurons instead of 1, and we average over 2? And what if we take 4 neurons, or 8, 16, 32, and so on? So we have different clusters, and we just clustered these. One single neural network unit, like a circle, would be a cluster of 8 silicon neurons. And if you calculate the coefficient of variation of these clusters, you see that it gets smaller and smaller and smaller. It goes from 20 to 18 to 12 to 8. You can also integrate over time. You can average over space, but you can average also over time. So if you average over time, also your CV goes down. There's a limit. You cannot go down to 0. Even if you use half of the full core, like a whole 128 neurons, we still have a coefficient of variation which is about 0.9. So it's not optimal. Once you have these numbers, you can convert them to equivalent bit resolution. So the color code here is the equivalent bit resolution. So you can go from 4-bit resolution to 14-bit resolution. 14 bits is very expensive. You would have to use half a core just for one single unit. But if you can get away with 8 bits, 8 bits is maybe 8 neurons or 16 neurons. So you could have a cluster of 8 neurons to have an 8-bit accurate ReLU unit if you really needed to. So this is one way to cope with robust computation. You can just average over clusters. You pay because that's area, and area in chips is money. So you pay by doing that. You cannot scale to large networks. If you only have 256 neurons, then if you're using 8 per unit, then you can only have a handful of neurons in your network. But it's one way of reducing variability. The other way is to look at how biology uses these neurons to represent signals. You don't necessarily have to use them as a ReLU. Actually, what happens in biology is that the neurons are tuned to some feature. This is an example of visual tuning. So the neuron is tuned to a particular orientation of a bar flashing on the screen. And if it's the optimal orientation, it will fire with the maximum firing rate, which is 50 hertz. very, very slow. And if it's a non-optimal orientation, it will decrease its firing rate all the way to 0 if it's like orthogonal, right? And these tuning maps are everywhere in the brain. So there is tuning maps for visual signals, tuning maps for auditory signals, for touch, for pressure signals. And there's theories showing that if you have these tuning maps, of course this is one neuron, and then you imagine you have the next neuron will not be tuned to 0 degrees, it might be tuned to 10 degrees, and so it will have a slightly different tuning curve, and then the next one will have a slightly different tuning curve. So the whole population will cover the whole feature space. It can represent the whole feature space. And then by combining the collective output of all of these units, you can get a very, very precise estimate of the real feature, the value of the feature, whether it's the angle of the orientation, whether it's the frequency of the tone that is being played, and whether it's the position on the skin. You can really get a very, very precise element, even though you have many imprecise elements working together. So by collective computation, population coding, you can get really good high precision. So you don't need to only average. If you have these tuning curves, the representation of a signal is really, really important for doing that. And this is an example of visual tuning. So all the colors here represent different orientations taken from the macaque visual cortex, just to show you, that in all parts of the brain we represent signals like this. Of course, our neurons also represent signals like a ReLU. If I press on a tactile sensor, the pressure is encoded with the frequency of the neurons, but then there is also this way of representing signals in which the position of the neuron represents the value of the feature. And we've been reproducing this with our chips as well. So this is data that Elisabetta took when she was doing her PhD, where we were inspired by the experiments of Hubel and Wiesel, and we redid that. So if we just had a feed-forward connection, just by connecting them with feed-forward, we get the green plot. So we do get a bump just by construction. We just have different angles that are contacting the same cell with different weights. But then if we turn on what I will show you is as a winner-take-all network, we get the same type of behavior. We get sharpening of the tuning curve, selective amplification, and suppression of the distractors. So this is something that we verified. Our hardware is compatible with these ideas, and representing signals in this way allows us to do robust computation. And then there's many more advantages to using population codes than just getting these precise outputs. Actually, there's all these false myths, right, that tell you neurons are slow. Why should you go with spiking neurons? They're very slow. If you need to react, fast reaction times, if you're a drone trying to avoid, a tennis ball, it will never work. It's not true. If you have populations of noisy neurons, they can have very fast response times. Tatiana Tomachenko has data from real neurons showing that you can speed up things by even a factor of 50 just by using a handful of neurons instead of a single neuron. So you can really get microsecond reaction times even though your neuron is taking milliseconds, single neurons taking milliseconds to react. If they are heterogeneous, if they're all different, some neurons will be close to firing, some neurons will be far away, so the ones close to firing will react quickly. Another myth is that if you need high accuracy, you need high firing rates. And if you have high firing rates, then what's the point? You're going to be burning power. That's not true. Sophie Deneuve and Christian Markens show that you have sparse neuropopulation activity. You can train these clusters to fire very sparsely, like once a second, but encode signals with very high accuracy. And again, if you want to look at these papers, you can just click on these links. I'll give you the slides, and you can go to the theoretical demonstration. Neurons need to be accurate to propagate signals across multiple layers. If you have a deep network, you want neurons to be accurate. That's not true. Indeed, not only it's better if they are noisy and heterogeneous, they have to be heterogeneous if you want to recover small changes in the input. And this was demonstrated by Van Rossum already more than 20 years ago in one of his papers. So using populations really gives you many, many more advantages. You have many more benefits than just having more precision. However, remember, there is always no free lunch. I'm not trying to sell this. There is always this problem that you have to use more area. And if you have a fixed area, that means that you have to have small networks. This network cannot be too large. Finally, learning was the other way to compensate for variability. But here I'm showing you how heterogeneity even helps learning. So this is an example of a single layer, one layer neural network where you have some input signals, and then you have a binary classifier, standard one, 1956 perceptron, and we were using it to benchmark, the standard benchmark that any AI computational scientist asks you. How about your accuracy on MNIST? And you can imagine the silicon neuron has different mismatch in the synapse. The neuron itself is noisy, it's sensitive to the variability. So when we try to train our synapses with in this one layer network, we got something that was like around 30% accuracy. And even this very simple network, if you do it in a computer simulation, you get at least 80% accuracy. Of course, if you have a CNN, you go all the way up to more than 99. But a simple layer like this already gives you, in a computer, in a bit-precise computer simulation, gives you 76 or 83, I don't remember. So this is laughable. They would kick us out of NeurIPS if we went with this idea, saying, look, we can do classification of MNIST with our chips. But then we went back and looked at the literature, and from the 90s, we found that there are these ensemble techniques, boosting and bagging techniques, that rely on independent, weak classifiers. Weak is the term they use. I use crappy classifiers, if you have 30% accuracy. But if you have many of these neurons, and all of these neurons are different, then you can combine their output, and by adding more and more neurons, the theory says you should increase accuracy exponentially, or you reduce the error exponentially. And that's what we tried to verify with our chips. This is Fabio Stefanini's work when he was also a PhD student with Elizabeth and I. So he increased the number of neurons and then clustered, clustering, and the accuracy indeed goes up as expected. Because there are some correlations, it's not completely independent, these neurons. We don't see the exponential, but we do see the trend to go up. So if we have enough neurons, we can really start to be competitive with the computer simulations of AI engineers. So this is just to tell you that if you have learning and if you have variability, again, you can use populations of heterogeneous neurons to improve your accuracy. And we've been showing that. So this is just a slide with some examples. If you're interested, this is just to tell you we've been trying these types of things with spikes in input, patterns that, to us looks like just different noise, but you can recognize this noisy pattern distinguish it from this other noisy pattern through excitatory and inhibitory neurons, clusters of those that are noisy, using standard computational methods that have been proposed in the literature by colleagues, by Nicola Brunel, Stefano Fusi, and others that do the theory, and then we can map that theory into hardware, and we verify that that actually works on hardware. Just to hurry up, I still have a few minutes, I think it's 20 minutes, right? So I can tell you also what other things can be done with these chips. Again, remember, there is basically a row of neurons and a row of neurons, and then the synaptic matrix. If we connect the synapses in a way that only the first row is connected to some synapses, and then they are fed back with recurrent connectivity like a Hopfield network, and we do it for another population with recurrent connectivity and another one. We can create, just by construction, attractor networks. Typical Hopfield networks, like these would be the representation. And then you can imagine that this synaptic matrix could represent the picture of a cat, this synaptic matrix, or the memory, if you want, of a cat, this one, the picture of a dog, and maybe an airplane, and so on. So then whenever you stimulate that particular structure, with maybe a partially occluded picture of a cat, then that population will start to fire. But the property of an attractor is that it remembers, what the stimulus was. So even after you take the stimulus away, the activity doesn't go all the way back to zero. It drops because you're not actively driving it. So the average firing rate goes from 50 hertz to 12 or 15 hertz. But still it stays there. So you have the memory of that input. If you turn on a different input, because of the global competition, there's a global inhibitory set of neurons, you switch off the previous attractor, you turn on the next attractor, And then even after you take the input away, it stays there. And if you turn on the third input, you switch off all the other ones and you turn on the third attractor. And then even after you take your input away, it stays there. So this is again to show you that you can build memory elements that keep the information on forever until you give some inhibitory input. With this, despite the fact that you have such huge amount of variability. If you look at any one of these neurons, it's going to have a very different firing rate. But because we're using a population, we have a robust attractor that's more robust than the noise in the system and will keep everything there. And again, it follows the theory of attractors from Hopfield, from Sompolinsky, from Daniel Amit, and so the midfield theory from Nicolas Brunel, more recent, and so on. So all of this is verified both experimentally with data, but also we reproduce the theoretical concepts of attractor networks using this. And in this case, you see we have 3 populations of neurons that are interacting through a global inhibitory population, which then inhibits everyone back. If you think, if you extend this to more than 3, if you have many, you could think of this as a winner-take-all network. So you could represent many different features. It could be orientation, it could be frequency tuning, it could be cat versus dog versus airplane, and so on. And then these populations of neurons would be competing among each other, not just 2 or 3, but you could have, in this case, we have 128 neurons, so we could have up to maybe 64 different features if we use just clusters of 2. In this case, this chip was a 128 neuron chip. We were using the last few neurons for inhibition, and then the other ones we were just giving different bumps in input. The blue dots are the input, the black dots are the output. If you notice, the inputs differ by a very tiny amount. So they're like 180 hertz and 220 hertz or 210 hertz. But the output is highly different. This is this selective amplification property of the winner-take-all network that is verified theoretically and now validated experimentally. And I think I should have a video. Let's see if this actually works. So what you see now is the input to the winner-take-all network on the top diagram and the output of the winner-take-all network on the bottom diagram. So if you notice, there are 2 bumps in input. One is a slightly higher amplitude than the other one, and so the winner-take-all already starts to suppress the loser and amplify the winner. As time goes by, these 2 bumps will become equal in height, and then they will swap. Around 3 seconds they're equal, and then they swap. So I want you to pay attention to when the simulation, the recording of the chip output gets to 3 seconds, because that's when the winner-take-all has to make a decision when it's very ambiguous. What's happening if the inputs are identical? And again, this is recorded from the chip. There is no computer simulation anywhere in the loop. It's just spikes going in the chip and spikes coming out of the chip. It's something we could do in the lab, actually, with the Dynapse if we wanted to try that. So you see there's a clear winner here, but the bumps are getting closer and closer. And so now that they're about similar, there is ambiguity also in the winner-take-all. The winner-take-all shows both. And then as soon as there is a small difference between the bumps, the winner-take-all switches and amplifies the winner and suppresses the loser. So this is a highly nonlinear operation that can be done using these circuits. But the interesting thing is that if you think about it, in our brain, we only have neurons. We don't have filters and then logic gates. So the same computing substrate, this is an example of the auditory system, but it's true for all perceptual systems. The same computing substrate is the same one that we have at the peripheral part of the nervous system, the outer ears, the middle ears, the inner ears, all the way up to the brain lobes, the auditory cortex. And if you think about it, we're using the same neurons to do filtering. In the auditory system, we do frequency filtering. We selectively amplify different frequency bands. So this is all sort of filtering things that you would do with op-amps if you were an electrical engineer. And then all the way up here in the auditory cortex, we are processing semantic information. We are trying to distinguish, the words, the sentences, the meaning of a whole sentence. And these are symbols. We're doing symbolic manipulation. And so the same hardware is doing all of this. And if you think about it, what I showed you, the winner-take-all, is actually something that can do that. If we decrease the coupling strength of the winner-take-all, we can do filtering, we can do linear operators, we can amplify, we can do locus invariance, we can shift bands, and so on. And if you increase the feedback, the positive and negative feedback of the winner-take-all, you can do this nonlinear operations like selective amplification, memory, attractors, and so on. So this is something to keep in mind. You don't need to have analog filters, and then you need to have a CPU. You could use the same hardware to do both, to switch smoothly from analog to symbol manipulation, from processing waves of signals to actually distinguishing different features or different objects. And we can do that, again, with the winner-take-all. This is, again, data from the dynapse. If you have two bumps in input, which are the black lines, if you are in the filtering linear domain, you can either merge bumps, or if their bumps are separated, you can have two bumps. You basically, you can reproduce the inputs, you can clean them, you can do some noise shaping and so on. But if you increase the synaptic weights, then you can actually do Q integration. This might look like a single bump that has a mistake in the center. So this is a nonlinear operation. So Q integration is something important for processing signals. Or you can do the standard winner-take-all that I showed you, that can amplify slightly bigger inputs and suppress slightly smaller inputs completely. It's a high gain nonlinear operation here. So the same thing can be done using the winner-take-all network. And this is, again, data showing that it's another way of showing the same data. If you send inputs with these shaded blue lines to increase, input A versus input B, so that would be the blue versus the orange. In your linear processing mode, you just shift, you just follow the input basically. If you stimulate blue, you get blue and you suppress orange. If you stimulate orange, you get orange and you suppress blue. And then if you stimulate the orthogonal patterns, green and red, you stimulate red and you stimulate green and suppress red and so on. But again, if you increase the feedback, if you make the gain stronger, you go into this discrete way of manipulating objects. So as soon as you present the blue, it goes into the blue mode and ignores everything else. If you present the orange, it kills the blue and goes into the orange mode and remembers it even after you take the input away. So it's like it's in attractor mode. And you can keep on doing that. And even if you present these orthogonal patterns like distractors, they will not be strong enough to make the network forget that it was stimulated by an orange or by a blue. So this is again showing you that you can do symbolic manipulation and filtering just by using exactly the same network but only changing the parameters, which can be changed at runtime. So you could say, now I'm in filtering mode, now I'm in symbolic manipulation mode. And to give you an example of a symbolic manipulation network using this winner-take-all, because we heard about Ising machines from Luke last week, I wanted to show you this nice example that Hisham, a student of mine, made, showing you that you can use these winner-take-all networks to solve Sudoku. So how many of you know the Sudoku rules? Okay, so I don't have to explain that. Then you can see, you can put in every one of these nodes a winner-take-all network that has 9 elements, 1 to 9. And so that means that only one of those will win. So you can only have 1 digit per square. And then what you can do is you can connect with inhibitory connections the ones of this node with all the ones of the row, all the ones of the square, and all the ones of the column. So if there is one winning in any one, it will suppress all the other ones. And the same with all the other digits, 2, 3, 4, and up to 9. And then you can initialize randomly the network. So there will be cases in which there are conflicts because of the random initializations. And because of these winner-take-all networks, iterate and excite and inhibit each other, there will be some dynamics running in which all of these spikes will try to find a globally consistent solution, and only when everyone is happy, when the winner is the correct winner and it's not being inhibited by another winner, then the network will stop. And so here you see, if you randomly initialize a network like this, you will have a huge number of mistakes, so invalid outputs. Through the first few spikes, you decrease really dramatically the number of mistakes, but still it takes some time for the network to converge. So this is an example of showing, of course, these networks oscillate, and through oscillations, they sort of explore the state space and then find the global optimum. So this is an example of an Ising machine that is implemented using coupled winner-take-all networks that oscillate. Very similar to the ones that Luke was showing with winner-take-all circuits, not through spiking neurons, but he was showing winner-take-all analog circuits to do the same type of computation. And this idea of using winner-take-alls and coupling them together to go from one state to the other can be extended to a more generic framework, the one of finite state machines. So a finite state machines, according to Wikipedia, is a mathematical model of computation that can be used to design both computer programs and sequential logic circuits. If we can implement a finite state machines with spiking neural network, then we can implement any type of computation that is found, everywhere around. Finite state machines are everywhere, from your washing machine to your car to your computer. And this is showing you how you can actually do this. Is an example of a finite state machine. Finite state machine diagrams typically are like this. You have a state and then an external input. And this is the simplest possible finite state machine, which says, if I'm in state 1 and I receive input X, I should go to state 2. If I'm in state 2 and I receive input X, I should go back to state 1. So this type of state machine you can implement with a winner-take-all network, in which you have two clusters of neurons and one inhibitory cluster. If they're connected in a recurrent way, they are attractors, right? They self-sustain each other. If I'm in the red state, I will excite the red state, which will excite the red state, and so it will win both here and here. So the red state will persist always. If I'm in the blue state, this will become the winner, it will suppress the red, and the blue state will persist always here. But then if I stimulate, if I bias the competition and from an external input I stimulate, for example, the red state, even if the blue state was winning, because the red receives an external input, it will become the winner, which then will drive the red one here, which will make the blue lose, and then again it becomes persistent. So I can do competition from outside stimuli, but also the outside stimuli can always be one stimulus. I cannot stimulate with three different symbols. It's either X or on one side or X on the other side. So I need a winner-take-all also for the external inputs. And by connecting spiking neurons in this way, you can really show that you can have these populations of neurons spike whenever you send stimulus 1 or stimulus 2, so X to the red or X to the blue, you switch depending on where you were. And so here you have these raster plots that show you how you can implement this finite state machine using spiking neurons. This is a very, very simple example, but Emre and Elisabetta and others show that you can implement extremely complex state machines with many, many states and actually use that to reproduce a cognitive experiment that was done on monkeys, in which the experimentalist was saying, okay, the monkey is looking at the screen. If it sees a red cue, it has to follow these rules. If it sees a blue cue, it has to follow a different set of rules based on what's happening on the screen, and it has to press the button A or button B. So if then else can actually be done with this. And it's something that's used to test probe cognition in monkeys. And we reproduce the same exact experiment with DVS looking at a screen, looking at the red cue or the blue cue. And then the chip was going, saying, if I see bars moving one way, I press the A button. If I see bars moving the other way, I press the B button, depending on the instruction. So you have to have memory, attractors, and then you have to do the state machine. If I'm in state 1 and I receive this input, I do something. So this is just to tell you can implement also complex state machines using spiking neural networks. And Dongcheng Liang, who is also here, he actually put that on a robot, and he said, if I'm going straight and I see an obstacle to the left, then I turn right. If I'm turning right and I don't see anything, then I stop turning. And he made something that you really could navigate and follow maps using the same idea of state machines. which you can also find here in these papers. So to go towards the conclusions, we have these chips. We can use them to understand the brain, but we can also use them to do interesting, type of applications. The advantages are they're very low power. So the whole chip, if you think about it, it's going to take less than 1 milliwatt. It's very low latency, but the disadvantage is that it takes, if you need a large network, you'll need a large chip, which is very expensive. So it's a high area. It is highly variable and noisy. As I told you, we can improve, but we cannot get 32-bit floating point resolution at all. I mean, the max we could get was 14 bits, but that was already using a whole half a core. So this is a problem with these chips, and they are not very accurate if you wanted to compete with bit precise digital classifiers, deep networks. This is also something that would not work. So where can we use these chips? We can use them in closed loop sensory motor processing. If you have a motor controller, if you have to control the temperature in a room, or a drone that has to navigate, these types of things are ideal. And they're not ideal for number crunching. If you have, again, precise data on a data sheet, or if you want to really control with high accuracy timing of things, this would not be the best technology. Anytime something is already digital and stored on a hard disk, then that rules out already the use of these chips. These chips are good if you connect them directly to the sensor and you do in-sensor, in-memory computing. And in addition to that, there's actually a very big challenge, which we also heard from the talk last week, on what is the computational environment to program these chips. How do you program a chip to do a complex task? There is no established method yet, but that's also a generic problem. How do animals program their brains to do if then else? If I'm hungry and then there is the Mensa there, I turn left. But if I'm not hungry, I just go right. All of these things, there are these state machine theories, but there's nothing well defined. And programming these spiky neural network chips is really problematic. It takes a huge amount of time. There is no PyTorch or Java or Python for these chips. You really have to think in terms of networks and maybe attractors and winner-take-all networks and connect those together. So that's a challenge. But we have been trying to apply these to different types of problems, and many different problems related to biosignal processing. We think that's the low-hanging fruit. And just to show you a very, very simple one in the last minute, I'll show you that you can do really interesting things even using small networks. And this is something that Elisa, who is also supposed to come, hopefully, she's having problems with her visa, but maybe she can make it, has done already some years ago in 2019. So the idea is, if you are an amputee and you want to control a prosthetic device, you can use the muscle activity of the left of your arm, whatever is left from your arm, to control then the robotic hand. This is Elisa's hand in this case. Fortunately, she's not an amputee, but she's measuring her muscle activity here, sending that to the dynaps, which has these spiky neurons, converting the signals into spikes first, sending the spikes, and then using a reservoir network or a network of excitatory and inhibitory neurons with a one-layer classifier, one single perceptron layer, the 1956 classifier, to say whether you should open or close your hand. And so again, you see that you convert these signals to spikes, you get the spikes on the oscilloscope, you have up and down spikes depending if your signal is increasing or decreasing, and then you can send it to your spiky neural network classifier, simple perceptron. And it actually works reliably well. If you even compare to support vector machine or linear regression, you get competitive results. So this could actually work. And again, if you integrate this chip, if you do it in a well-engineered way, it would really be a 1 milliwatt chip that you could, like the size of a coin. So you could really put it directly on the sensor, directly here, and control your robotic prosthetic device without having to wear a backpack doing the classification. As I said, there's many more applications where we did similar things for the ECG, for the heart, for PPG, and we're trying to extend in this domain. We try to do that in cases where you cannot use your Apple phone or your Apple Watch. For example, for animals, for babies, for elderly people that, you just have a band you wear, you don't need to worry about it anymore, or recharge it. And if something goes wrong, it calls the nurse, it calls the family, and if there's some anomaly somewhere, it just makes an alarm. So these are the type of applications we think are the simplest one to start with these types of chips. So to conclude, conventional AI has some limitations. I didn't mention it, but you all know about the sustainability and how it's becoming unsustainable. There are these new emerging memory technologies, ReRAM, ferroelectric, spintronics, that can really be used to improve the size of our chips if we could replace them. Neuroscience has been making tremendous progress. From the 90s when I started being interested in it to today, there's a huge amount of knowledge that now we can use to do computation using spiky neural networks, nonlinear synapses, dendritic compartments, and so on. And hardware implementations of spiky networks are starting to show their advantages in biomedical applications, for example, but also in other domains. So this is the perfect time to start looking into this type of research and take things to the next level. This is an editorial from already 2018, but I think it's still valid today. Big data needs a hardware revolution. So if you look at the fine print, it says software companies are making headlines, Microsoft, Meta, Google with ChatGPT, OpenAI. But research on computer hardware could bring bigger rewards. So this is just also to emphasize, if you are interested in understanding analog mixed signal circuits and building these spiky neural network chips, this is the best time to start looking into that. And with that, I'd finish. I just want to acknowledge this is the team. So Elisa is going to come. Chiara De Luca was here last year as well. There are some students, many previous students that went through the institute, and many also collaborators, including Elisabetta and Chiara Bartolozzi, who are here at this workshop. And some funding organizations that funded the research. And mostly, thank you for your attention.